The bright line spectrum is unique to every element because it is very specific wavelengths or colors of visible light that are emitted by an element when its excited electrons return to the ground state. So let's take, for example, an element that has, we'll say, 2 valence electrons. If one of these electrons absorbed energy, it would bounce from the first principal energy level possibly up to the second. However, that electron and its excited state can't stay there very long. Think of it like when you drink a cup of coffee. You might be kind of jittery and excited for a little while, but after a couple of hours, you're going to crash. You're going to fall back to your normal state, or possibly even less than that, though that can't happen with electrons. As that energy is lost by the electron, it's actually lost in the form of light. The wavelengths or colors of that light are specific to the element because each electron has a specific amount of energy. And when it loses that energy, the electron, that's supposed to be the nucleus, the electron goes back to being in that first principal energy level, or its ground state. All of the electron configurations given in the periodic table, take for example magnesium, are given in the ground state. It's also for an atom of magnesium, which is why the number of electrons, when you add it up, totals 12, which is also the atomic number or the number of protons. If magnesium were to have an excited electron, one or more of those electrons would jump up to a higher energy level. For example, it might look like this. So what happened is that one of the electrons in the second principal energy level actually jumped up to the third. So we still have a total of 12 electrons. It's still an atom of magnesium, but they are no longer all in the ground state. So this would be an example of an excited state electron configuration.